the poles will interact with the stator twice. And remember, this interaction comes as electromagnetic forces of repulsion and attraction, and that gives rise to the frequency of vibration. In North America, most machines are running at 3600 RPM, and that means a line frequency of 60 Hertz. If you monitor the vibration of the end winding, it will come to 120 Hertz, quite exact. If you are in Europe or in Asia, the generator turning at 3000 RPM and giving you the line frequency of 50, and you can distinctly see that SEW signal corresponding to that to be 100. I have both examples to show you in a little bit later. Now, so far we said this vibration is inherent in the machine, and second, it is growing in amplitude that start to destroy the insulation layer. Okay. Now, why is the vibration amplitude growing? Well, looseness. New generator, the wedges are very tight, and there is a structure called the ripple spring to hold everything together. And this ripple spring is made with fiberglass. Now, it's supposed to be very stable, but with time and thermal loading differences day and night, and sometimes large surges cause structures to move, and sometimes it creates cracks and therefore loose parts, and so this looseness is inevitable. You can't avoid it. But another thing is that it doesn't happen overnight. All we have to do is to keep on monitoring it and continue to compare with the baseline value. Now, where does that baseline value come from? The first time you have a chance to install an online monitoring vibration system, then you grab the time domain or the amplitude of this vibration. Just the example I show you here. Now, what would you decide when would you decide whether it's normal or not normal? By the way, SEW signal is not absolute. We don't call it good or bad. It's relative. It is a trending exercise. Now, there is though a comparison between the size of the generator. So you remember I showed you the example about the burnt ending, and that comes from a small hydro plant of 10 megawatts. And with a machine so small, the current is not large, and is related to the electromagnetic forces resulted from that will be relatively small. So such a machine, we can expect the baseline value to be about 10 micron, 8 micron peak to peak. But if you compare a very large generator, like this example, by the way, came from Perky plant in Marshall, Texas, owned by AEP. And this is the actual signal that we recorded from the machine. Now, I like to point out a few things. And first of all, if you look at this little counter, the frequency, it is clearly very close to 120 Hertz 2 times the line frequency of North America. And another important thing I like to point out is the peak-to-peak amplitude. This peak-to-peak amplitude is a little bit higher than 100 micron. Remember what I said? It has something to do with the size of the generator. The larger the generator, the bigger will be the current, and the bigger will be the electromagnetic forces, and therefore the vibration peak-to-peak performance. Now you understand that this is 2 times line frequency. Now I want to help you make the analysis easier. First of all, if it's related to looseness, and looseness does not happen overnight. So it will not be very effective to try to monitor it every minute. For example, you don't expect things to happen like that. However, it might be a good idea to at least take a sample every hour. And each time you take the sample is only 1 second, because if you are talking about a sampling rate, by the way, the rule of the thumb is sample at least 10 times the target signal frequency that you expect. Okay, so in this case, since we want to monitor this 120 Hertz SEW signal, we set the sampling rate to 1200. Okay? Now, the benefit of that is to reduce the amount of data that you have to collect. And frequency, we suggest, you will still be able to see the vibration amplitude dependence on loading and also with temperature. As a matter of fact, the online monitoring tool is not just an alarm and alert tool. It allows you to diagnose the health of your generator, and I will be discussing more about that. To show you that this SEW signal is consistent over a long period of time, I have included the data collected from the hydro plant in India. So this is also a good time to discuss about the features of our monitoring trending tool called the TGI. In TGI, it's a very flexible tool. It allows you to prescribe any starting point, any stopping point, and the software will grab all the data collected during this period and allow you to perform 2 types of analysis. The first analysis is time domain. However, if you look at this view graph, so much activity is going on. Nobody can read anything from it. However, if you perform a fast Fourier transform, here distinctly came out is a peak at 100 Hertz. So again, since the example came from India, so it falls exactly at the 2 times line frequency of 100 Hertz. So there you go. This is a further proof that SEW, it is dependent on the line frequency and is quite consistent. Then the next view graph explains the function, the benefit of this TGI. Again, you can go to the complete database, select the starting and stopping point. In this case, we are talking about several weeks of data have been collected. Now, I would like to point your attention to one of the channels, namely channel 1. A group of 8 sensors have been displayed here with different color code. Now, I hope you can see channel 1, which is the top one, has from time to time close to the alert limit of 10 micron. Remember, we set it at 10 because we are dealing with a small machine. Now, if I were to compare that with Perky, which is something like a 720 megawatt, and the vibration amplitude found to be a little bit more than 100, that is quite okay. So the rule of the thumb is this: install online monitoring tool and collect the baseline value and use it as a reference. Then constantly compare with the collected data. Now, we normally work with the plant people to set the alert limit to be 2 times the baseline value. So, for example, let's say your baseline is 100 micron. So you should not get nervous or uptight about when the thing is slightly above 100, 140, 150, and that because this is loading dependent. So if you increase the load of the machine, the vibration will turn up a little bit more. Now, to show you that the sensors are working, when you collect the data every hour, you will be able to see the pattern of a daily load cycle. During the day, the load is heavier, and in the evening, the load is reduced. All these can be shown on the SEW data that you collect. Now, in this case, we see channel 1 close in to 10 micron line, get up there, came back again and again, and finally it crosses the line and became 14. Okay, so now this is no cause for alarm. We are not going to shut down the machine when it does that. It's just an alert signal telling the maintenance engineer to pay some attention to channel 1, and that's all. Now, subsequently, this is still not shown to be an alarm. To show that this SEW is very consistent, I have made another plot called the waterfall plot. And what it is a distributed fast Fourier transform. And we took 3-4 weeks of data, and then we plot the center frequency of the main vibration signal. Once again, you see consistently all days during the period, there is no deviation. Consistently is this 100 hertz. Now, picture also show some harmonics. These harmonics might be due to the sensor itself, might be due to other problems like soft foot in the generator. Now, that becomes another issue which we have to deal with separately. So why do we feel vibrofiber is the most appropriate thing to do to solve this SEW problem? Well, it is made with glass. It's a glass fiber, and it doesn't contain any conducting parts. It is made with passive material. That means the glass, the